Hey everyone, so this is now video 3. We're going to be talking about the effects of substituents and how we can do some synthesis of molecules related to aromatic substitution. Okay, so let's go to the next slide here. All right, so in the previous videos we were talking about how to add substituents on an aromatic ring. We started off with benzene, and we were saying that we can add all of these electrophiles onto the benzene ring, right? And then we saw the effect of having a substituent on a benzene ring, right? Whether the electrophile is going to add ortho, meta, or para to that substituent. What if you have a situation, though, where now you're dealing with multiple substituents? So basically, if you look at this example, let's say I'm trying to take this molecule right over here, and notice that there's multiple substituents, right? There's a methyl group here, and there's a nitro group. And both of those substituents have an effect on the ring, right? Whether they're ortho, para, or meta-directing. And let's say we're trying to brominate this molecule, right, at a BR. The question is, where's the BR going to go? Is it going to go ortho, meta, para to relative to these substituents? The first thing you need to ask yourself is, okay, well, what directing effect does, let's say just looking at the methyl first, what directing effect does the methyl group have? Well, we know that methyl groups are electron donating to the rings, so they're ortho-para directors, right? And a nitro group we saw was a meta-director. So just looking at the CH3 group, if it's going to add ortho and para, it's going to add at these positions. Those are ortho to the methyl group, and at the para position. But the para position is already occupied, right? So it's not like there's going to be another group added to that position. So right now, the only choices we have are these two ortho positions, right? Now, if you look at the meta-director, which is the NO2 group, the groups are going to add meta to that group. And when you look at the meta position relative to this group, it's also these positions, right? Aren't these ones that I just highlighted and circled here meta to this NO2 group, right? It is. So that kind of reinforces that both of these groups reinforce each other, because the substituent is going to add on the exact same position, right? The BR is going to add at the exact same spot. So both of these groups kind of reinforce each other, right? They direct the substituent, the electrophile, in this case the BR, to be at the same location, right? Which are these locations right here. So this is a pretty easy synthesis, right? Because these groups are pretty much going to direct to the same exact position. All right, what if you have a situation though where in some cases the directing effects of the substituents on the ring are going to compete with each other, right? So if you look at this example, I'm trying to do a nitration of this compound, right? And right now I need to ask myself, okay, what are the directing effects of the substituents here? This OH group, right? That OH group is going to be ortho-para directing, right? It's a pretty strong one too. And the CH3 here is a weak ortho-para director, right? So the question is, okay, if I want to substitute at these positions relative to the CH3, or do I want to substitute ortho relative to the OH? Who's going to win? In general, the rule of thumb is that the stronger group will dominate the directing effect. So because the OH group is a stronger ortho-para director than the methyl group, right? The methyl group is a weak ortho-para director. We saw that in the previous video. The stronger director is going to win, okay? And we know why an OH group is a stronger director, right? You guys remember that from the last video? It's because we have a lone pair on the oxygen that can donate electrons to the ring, right? You guys can do resonance over there. You see how the electrons are going to end up on an ortho position, right? And those electrons could be nucleophilic towards an electrophilic, in this case, nitro group. So that's a stronger director than CH3, because CH3 doesn't have a lone pair to donate electrons. We know that a CH3 group or any alkyl group will donate electrons through hyperconjugation. Not as good of a director, right? It's pretty weak. Lone pair is way better. A lone pair next to a double bond is way better to donate electron density into the ring than just hyperconjugation. So if this OH group is going to be the stronger director, it's going to win and dominate, and therefore that's why you see the NO2 group end up ortho to the stronger ortho-para directing group. Okay? All right, let's practice a problem related to this. So in the following compound, identify the position that is most likely to undergo an electrophilic aromatic substitution reaction, an EAS reaction. So right now, the first thing to do when you look at this, if I had to add some sort of substituent on this ring, where is it going to go, right? If I'm trying to actually functionalize this benzene ring, which position will there be an EAS reaction, right? And the way that you start this problem is asking yourself, the groups that are currently on this ring, what kind of a directing effect do they have? Are they ortho-para directing? Are they meta-directing? Are they strong activators? Are they weak activators? Let's ask these questions one by one. We'll just look at each group individually one by one. So the first one you see is an OH group. We just said that an OH group is a strong activator, right? A CH3 group is a weak activator, right? We saw this already in the previous slide. And an NO2 group is that an activator? Nope, it's a deactivator. We saw that in the last video. Deactivator. And it's a pretty strong deactivator. Now, which one of these is going to win? Now, the rule of thumb is that the strongest activator is going to win. Deactivators never win, right? If you have an activator and a deactivator on a ring, the activator is always going to win, okay? And it's going to be the strongest that is available. So between the OH and the CH3, we saw in the previous slide that the OH wins. So the OH group is going to predominate as far as the directing effects go. And we know that this activator is going to be ortho-para directing. And if you highlight the ortho and para positions relative to the OH group, this position and this position is ortho to the OH, and this is the para position relative to the OH, right? So these are ortho, O and O, and this is para. But you guys can see that the ortho position over here is occupied, and the para position is also occupied. The only position that isn't occupied yet and available for substitution, for putting something on the ring, is this ortho position right over here. So this is available. So that position right over there is available for functionalization. So that's the position that's most likely going to undergo electrophilic aromatic substitution. So bottom line is, if I had an example problem where I just showed you, okay, here is your molecule. I'm just going to redraw what the problem gave us. And I said, okay, you have some electrophile, E+, right? Where is this electrophile going to attach? It's going to attach at that available position, which is right over here. I'm going to redraw everything the way that it was, CH3, OH, and the electrophile is going to go right over here, which is ortho, right? This is ortho, O, or for ortho, to the OH group, which is the strong activator. Okay? Hopefully that makes sense. Right, just to kind of recap, what did we just do? We looked at the directing effects of every substituent on the ring, and we asked ourselves which one of them are activators. And then of the activators, because those dominate, which one of them is the strongest activator? And then once we figured out which one was the strongest activator, we looked at what positions were available to functionalize. And we saw that that particular position right over here was available. Okay? So I have some practice problems related to this, so you guys should give this a shot. Posted this on a problem set, and an answer key will be available. So give these a shot and ask yourselves which positions are most likely going to undergo EAS. Okay? Now, a couple of key things to keep in mind is steric effects. So I told you guys earlier that if you have positions that are competing with each other, like let's say you have an ortho-para-directing group, right? Like this alkyl group, you guys know alkyl groups are ortho-para-directing, right? So right now, if you look at this example, the ortho and para positions relative to that substituent are here. These are ortho, and this is para. And the question is, if I'm doing a nitration on this, where's the nitro group going to go? Is it going to go on the ortho or para position? And in the previous videos, I've indicated that due to steric reasons, the para position is the less sterically hindered position, right? The ortho positions are kind of crowded because this alkyl group is pretty bulky, right? So because it's bulky, it's taking up a lot of space. It's kind of crowding the ortho positions for it to be, substituted. So the ortho positions are a little crowded for functionalization. We'd rather have the para position that's more sterically available to functionalize. And therefore, usually if you're debating between ortho and para, you usually get the para product as the major product. Remember, the only time you ever get the ortho product as major is when the alkyl group is like really small, particularly like a CH3 group. That's the only case. Usually when it's bigger than a CH3 group, the major product is always going to be para. So that's just something to keep in mind, and you'll see that going forward. Now, let's say you have a 1,4 disubstituted ring, and both of the groups are ortho-para directing, right? Both of these are ortho-para directing. Well, you might ask yourself which of these groups is going to win as far as getting a nitro group. Is the methyl group going to win as far as getting the nitro group on the ortho positions here, right? The para position is occupied, so we don't even have to think about adding para. Or is the nitro group going to add relative to this activator? Is it going to be over here and over here? So you have these competing positions. Which one's going to win? Well, it turns out that the group that wins is the one that's the less sterically hindered, right? So the one that's not as bulky. So we clearly see that this methyl group is not as bulky as this one. And if the NO2 had to go anywhere, it's going to go based on whichever group is not as bulky, right? So these are way more sterically available ortho positions than the other one, right? So therefore, the major product here is going to be where the NO2 is ortho to the methyl group. Okay, so this is going to be the major product. Okay, hopefully that makes sense. Let's go to the next part of sterics, because sterics do play a role, right? Notice now these activating groups are meta to each other, right? And the question is, when you do a nitration, where is it going to go? Is it going to go, you know, at this ortho position, right, relative to the methyl? Or if you're talking about relative to this, there's another ortho position available right over here. Well, you know that this position and this position is pretty crowded right now, right? It's pretty crowded because of the isopropyl group. And the most sterically available position seems to be this position right over here, right? That's the less crowded position. So if I had to pick one of these, it's definitely going to be that position, and that's going to give you this product right over here. This one's going to be the minor. And honestly, if you're trying to put an NO2 group right over there, that is just way too crowded. Notice that ortho position is in between two alkyl groups. That's way too crowded. So this is pretty much not observed, trying to get an NO2 group right in between those substituents. It's just not going to happen. Okay, so don't even think about putting it over there. As soon as you see that a position is really crowded, that position is not going to get functionalized. You're not going to add a substituent at that position. Okay? Okay, so in the following compound, let's just do a practice problem related to this. It says determine the position that is most likely to be the site of electrophilic aromatic substitution. So right now, again, we're going to ask ourselves, what is the effect of each of these substituents for EAS? Let's just go one at a time. This is a weak activator, right? An alkyl group is always dubbed as a weak activator due to its hyperconjugating effect. An NO2 group is a strong deactivator. And remember what we said, that activators always win. Deactivators always lose. So even though this is a weak activator, it's going to win over the strong deactivator. And if you look at the weak activator, what positions are available to functionalize? Well, right now we got these two ortho positions relative to the weak activator, and we got the para position relative to the weak activator. Okay? Now, this is clearly occupied, so that can't happen. It's not going to happen there. And now there's a debate between this position and this position. The ortho position versus the para position is way more sterically available for functionalization. So I would say that para position is going to win over the ortho position because the ortho position is a little crowded, right? So this position is most likely to be the site right over here for electrophilic aromatic substitution. Okay, so just to kind of erase all of that, this is the best place to put a substituent. Okay? All right. There's some practice problems related to this. Okay, so you can try them out. Just make sure to, again, do exactly what I did. Go through each substituent. Ask yourself, is it a good activator? Is it a deactivator? Once you know if it's an activator or deactivator, figure out, is it a strong, weak, or moderate activator or deactivator? You guys know the activators always take precedence. They take priority. They dominate. And then once you find your activators, find out which positions are available to functionalize, and then ask yourself, well, which of those positions would we rather choose based on sterics? Okay, so that's basically what you're doing here. Okay, now, what if you run into a situation where you want to force functionalizing the ortho position? So that's going to be really tough because right now, if I try to get a BR at this position, it's super crowded, right? Look how big this terp-butyl group is. We know that alkyl groups are ortho and para directing, right? Ortho, and para directing. But if I try to do a bromination of that, it's just going to go to the para position. So how do we force it to go to the ortho position? Well, what if I use something called a blocking group? What a blocking group does is it basically allows you to functionalize the para position first, and it blocks the para position so that you have to force the ortho position to get functionalized, right? If you block the para position, the only other position available to functionalize is the ortho position, okay? So if you install a blocking group, then you can take the blocking group off, remove it, and then you have your product, right? Because right now, like I said, if I try to do this with BR2 and a Lewis acid, right now we know it's going to go to the para position, right? The product is going to be, this is going to be the major product, but we want this one. So we need to block this position. Block this position. Because if you block that position with some other group other than BR, then you throw BR2 at it, the only other possible option is the ortho position. Now, what are some blocking groups that we can use? I don't know if you remember back in that previous video, we talked about sulfonation and how sulfonation is a reversible process. That's actually great because if it's reversible, you can easily remove it after you add it, right? Concentrated fuming H2SO4 is going to add a sulfonyl group, but then under dilute conditions, you can just take it off and go back to the H. So that's really convenient. Because now we can use a sulfonyl group as a blocking group, right? So now if I use fuming H2SO4, it's going to add at the para position. Now we've blocked the para position. The only other positions available to functionalize are these ortho positions, okay? And now when you have BR2 and your Lewis acid, you're going to force the BR to go on the ortho position because the para position is blocked. And then you can remove the blocking group with dilute H2SO4. Just take this SO3H out, and now you're left with your product, right? So super convenient way to force a group on the ortho position when it's pretty crowded. So this problem asks, identify whether a blocking group is necessary to accomplish the following transformation. Again, we're going to go through the same process we did last time, right? We just asked ourselves, what is the effect of each of these substituents on the ring? Okay, because right now we know we need to add a BR to this. That's the new thing going from left to right. And the question is, okay, is this methoxy group an activator or a deactivator? We learned that methoxy groups are activators. This is going to be a deactivator, this acyl group. Right? And if you don't remember why these are activators and deactivators, go back to the previous video to review how to figure out which groups are activators and deactivators, okay? All right, so now that we know this is an activator, is this a strong or weak or moderate activator? Textbook says it's a moderate activator. I talked about that in the last video, but you could also say it's a strong activator. It's kind of in between, honestly. I think it's strong. Textbook says it's moderate. We'll just kind of go halvesies on that. But this group right over here, this acyl group, if you don't remember, look back on the video. This is a moderate deactivator. Okay? But we just said that the activators always win, right? So if the activators always win, we need to base our directing effect on the activator. According to this activator, the ortho positions are right over here, and the para positions right over there. And we need the BR at this ortho position. But right now, if we just take this molecule and add Br2 and a Lewis acid like AlBr3, it's going to go para, right? Because the para position is the less sterically hindered position, right? It's the most wide open position for functionalization. It's going to go para before it goes ortho. So we need a blocking group at the para position. Okay, the blocking group in this case is very much necessary. So what does that mean? That means that when I derive a synthesis for this molecule, we need to incorporate a blocking group. So right now I'm just drawing what the problem gave me. So right now we need some fuming H2SO4, or if you want, you can say SO3, H2SO4. I talked about that in a previous video, how you could use these reagents instead. Or you could just write it out that way to then get this. Oh, let me redraw that. That was really bad. Okay, so you're going to get an SO3H at the para position, right? The para position relative to the methoxy group, the activator. Now that you functionalize this para position, you can throw Br2, AlCl3, and now the only other position available to functionalize is the ortho position, right? And now you're going to take that blocking group off. How do you take it off? Just use some dilute H2SO4. And actually, if you use dilute H2SO4, you take the blocking group off. And there you have it. Right, this would have been great if we could just do this all in one step, but we can't do this in one step, right? We have to add the blocking group first to force it at the ortho position. All right, so with that practice problem, you should try these. It's asking the same question and says determine whether a blocking group is necessary to accomplish each of the following transformations. So try these on your own. Now, these are synthesis strategies. So right now, this slide is just showing you 10 different groups that you can install on a benzene ring using the reactions we covered so far. Now, you should commit all of these transformations to memory, right? Because right now, the only way you can do more complicated problems is if you know this first. So you should know this first before we do anything more complicated. Just know what reagents are going to accomplish which transformations, right? How do you get a Br on a benzene? Need Br2, AlBr3, right? How do you get, let's say this acyl group, right? That's through Friedel-Crafts acylation. We talked about a lot of those reactions in the previous videos. Make sure you know which reagents make different products, okay? Because then you're going to be using this for synthesizing different benzene derivatives, right? Like different stuff coming off of benzene. You're going to figure out, well, you need to know the reagents to do that, right? Pay close attention to the ones that are highlighted in blue, right? These transformations. Notice that these require multiple steps, right? We talked about these, so this is just a little bit of a review. If you want to reduce a nitro down to an NH2, we talked about what reagents do that. If you want to add, Br groups to this CH3, you can use NBS. That's kind of obvious. We learned that you can functionalize a benzylic carbon using NBS or Br2 in light, right? We also said that we can make this a carboxylic acid with KMNO4, or if you want, you can use some sort of chromium agent, right? Like instead of this, you can use Na2CrO 7 or CrO3, right? Whichever chromium agent you want, you can use that. Okay. But bottom line is definitely commit this to memory, okay? Because you're going to need this. And we're going to apply this to some problems coming up. Here's just some practice you can do to help you remember. It says identify reagents that can be used to convert benzene into each of the following compounds. So if you want to practice using this, this sort of schematic here and try to remember all the reagents and what you're going to make, this is a good practice problem that can get you to do that, okay? And I'll put that on the problem set for you guys to practice. This is another one where it says identify the product obtained when benzene is treated with each of the following reagents. Okay, so this is just another problem you can practice using this, this schematic here, this overview. Okay, so now we're going to use this toolbox of ours to synthesize benzene rings, okay? Now, when you're synthesizing benzene rings, you have to pay very close attention to where the groups on your product are, right? So if I'm starting with benzene and I'm trying to make this, in what order should I add my reagents to be able to get the Br and the NO2, the nitro group, at the correct positions? That's what you should ask yourself. Because you can't just add the reagents in whatever order you want, right? Because what if one reagent you use is going to add one group, and then that group is going to direct where the other group goes, right? You need to take that into consideration. You need to be very careful. Right now, you can see that these two groups are meta to each other, right? So they need to be meta to each other. How do you know they're meta to each other? Well, if you look at this group, what's the meta position relative to that group? It's right over here, right? There's an NO2 on the meta position of this. If you look at this, this is meta relative to that, relative to the NO2 group, right? This is the meta position. So you can just kind of deduce that by looking at it. But in which order am I going to add these? Now, notice that both of these groups are not meta directors, right? Like this is a meta director, but a Br is not. Remember, halogens are orthopara directors, while NO2 is a meta director. So which one makes sense to add first? Well, if I need to install a group meta, right, doesn't it make sense to install a meta directing group first? I would think that makes the most sense, right? Because if you, let me erase this. If you take a benzene ring and you treat this with HNO3 with some sulfuric acid, you're going to get an NO2 group. Doesn't matter which carbon you added in because they're all the same. But now that you know that this is a meta director because it's a deactivator, you can then make this with Br2 and AlCl3, right? Because now that Br group is going to add meta to the NO2 group. Realize if you did this the other way, it wouldn't work, right? If I did the Br2 first, if I did Br2 first, and then I did HNO3, H2SO4, to add the nitro group, where's the nitro group going to go? Well, Br is an orthopara director, right? So it's going to go para. We just said that usually if you're debating about ortho and para, it's going to go para. So the NO2 group is going to go para. This is not this, right? Those are not the same. So the order in which you add the reagents to make something really matters in this case, right? Now, sometimes you might have to change the directing effect for a group. For example, NO2 is a meta director, right? But you can actually manipulate an NO2, reduce it down to NH2. We saw that in the previous videos. And an NH2 group is now an ortho para director. And you could take advantage of that when you're trying to do a synthesis. You can change the directing effects of a substituent to be able to synthesize various compounds that are benzene derivatives, right? And here's just a table showing you how you can modify a bunch of directing groups to different types of directing groups, okay? For example, if I'm looking at this and I'm like, okay, I need to make this molecule right over here. Notice that these groups are meta to each other, right? The Cl and the amino group, the amine group, they're meta to each other. Just like in our previous example where the two groups were meta to each other. But wait a minute, both of these groups are ortho para directors. So how's this going to work? Like, if you install one of the groups, then the next group is just going to be para, most likely, right? So these are meta to each other. What do we do about that? Well, first of all, you know that the only way to install an NH2 group, at least to your knowledge, is to first make it an NO2 group, right? Right over here. So before you make an NH2 group, it has to be an NO2, right? And you guys know that an NO2 group is a meta director, which is great because if it's a meta director, you can install the Cl before reducing it down to the NH2. Right? That would be a pretty good idea, right? There's no reason that you should reduce the NO2, before adding the Cl, because that's just going to mess it up. If you reduce this down to the NH2, it's going to be an ortho para director, and the Cl is going to end up at the less sterically hindered para position, right? But we need it meta. So this just comes to show that, you can do a nitration first, right? That's the first step. That's step number 1. The second step, step number 2, is adding the Cl. That's going to install the Cl meta to the NO2. And then step 3 and 4 is now going to reduce the NO2 down to the NH2. Okay? And like I said, in most cases, changing the order of the reactions and reagents will change the substitution pattern on the ring. We saw that, right? This order really matters. Order really matters. You can't just add these in whatever order you want because you're going to get a different product. Okay? Now, there's a couple of limitations with synthesis strategies. For one, if you're trying to add an NO2 group or do a nitration on something that already has an amino group, you can't do it because what's going to happen is the conditions that are used for nitration is just going to oxidize this to an NO2. So if I throw HNO2 at this, HNO3 and sulfuric acid, you're not going to get this product. You're going to get this. You're actually going to oxidize the NH2 back to an NO2, and then the second NO2 is just going to go meta because an NO2 is a meta director, right? So you're not going to be able to do this. That's just one limitation, is you can't do a nitration on something that already has an amino group on it, okay? The other limitation there is to synthesis is you can't do a Friedel-Crafts reaction, like an acylation or an alkylation, on benzenes that already have deactivators on them, moderate or strong. If you have a weak deactivator like the halogens, it's fine. But if you have a strong or moderate deactivator on your ring already, you can't do a Friedel-Crafts alkylation or acylation. It's just not going to work. No reaction. Okay? So that's just another limitation you need to worry about. Okay, so why don't we now practice these concepts into a problem? It says starting with benzene and using any other necessary reagents of your choice, design a synthesis of the following compound. Okay, so remember the first thing we do when we're trying to synthesize something starting with benzene. The first thing you need to ask yourself is, you know, when I have a molecule that I'm trying to synthesize, which is basically a substituted benzene, you know, if I have two groups on this benzene, what's their position relative to each other? Are they ortho to each other? Are they para to each other? Are they meta to each other? Right? Notice that these two groups are meta to each other. Which means what? That means the first group that I should add on the benzene should be a meta director if I'm going to add a second group, right? And you know that, and both of these groups right now are not meta directors. But right now you know that you can manipulate this NH2, have it be an NO2 first, because NO2 is a meta director, right? And then you can add the alkyl group. Let's try that. Let's just see if that works. So let's do a nitration. Sorry, I'll just write it like that. It really should be written like this, NO2. I know that looks weird, but you see how the amino group is written like that? I'm just going to stay consistent because the nitrogen is what's really bonded to the carbon, right? Not the oxygens. Okay, now we need to add the alkyl group. And you guys know that I can't add this alkyl group just like this, right? Because that's going to undergo carbocation rearrangement. So it needs to be an acylation to avoid rearrangements. But wait a minute, didn't we just say that we can't do Friedel-Crafts acylations with strong deactivating groups? Let's just go back to our slides here. One of the synthesis strategy limitations was you cannot do a Friedel-Crafts alkylation or acylation with strong deactivating groups. You get no reaction. So this is actually not a good idea. This isn't going to work. Well, that sucks. That means we can't add the NO2 group first, can we? What if we add the other group first? What if we do the Friedel-Crafts acylation first? So why don't we add the alkyl group first? Right? Notice that it's 3 carbons, 1, 2, 3, 1, 2, 3. We need a Lewis acid, AlCl3, right? I forgot about that. Okay, so we did that. And I know you're like, well, wait a minute, there's no carbonyl in the product, right? But remember, we can get rid of that carbonyl through a Wolff-Kishner or, you know, the thioacetal Raney nickel or the Clemenson reduction we talked about, right? The zinc HCl. So we don't have to worry about that carbonyl. We can get rid of that. But right now, we need the NH2, right? Now we know that this group right over here is a moderate, a moderate deactivator, right? And if it's a moderate deactivator, deactivators are meta-directing, which means this group can go on a meta position. And this is the meta position relative to the group we have, right? That's meta. This is also meta, but realize they're just the same position. It doesn't matter. And I'm just going to stick to the one on top because it looks more like what we have drawn over here, right? So this meta position needs to be functionalized. So why don't we throw some HNO3 and H2SO4 at this to get a nitro group? Sorry, I'm just going to give myself a little more space here. And from here, we need to reduce both the carbonyl and the NO2 down. We got to get rid of them to make this. Now, luckily, you guys know that to get rid of NO2 and make it NH2, we just used zinc and HCl, right? And the second step is NaOH. Well, guess what? Zinc and HCl can also, that's a Clemmensen reduction, can reduce the carbonyl down. So look at that. You can get rid of both of those in one shot. That's just a practice example related to that. So remember, this couldn't work. This worked, right? This path all the way there worked great. Okay. Now it looks a little messy, but hopefully that made sense. I could rewrite this, honestly. Let me just rewrite this more neatly. Trying to erase all of this. Okay. So what was the first step we said we were going to do? The first step was we were going to do a Friedel-Crafts acylation. To get that. Then we're going to do a nitration. To get that. And then we were going to reduce this with zinc HCl and second sodium hydroxide to get that. Okay. All right. Now we got some more practice problems for you to try. I recommend that you give these a shot on your own. Okay? But let's just do one more example where now instead of 2 substituents on a benzene, we need 3. Right? We got this one, and this one. So how do you synthesize this from benzene? Now, you would think this one's a little more complicated, but really it's not that bad because you guys know when you do a synthesis problem, you should always start by doing some retrosynthesis. At least maybe one retrosynthesis error, right? I told you guys that you don't have to do retrosynthesis all the way, but at least think about retrosynthesis for at least one step, right? Go backwards one step. Now, if I'm going to do a retrosynthesis of this, I'm just going to pick which one of these I want to remove. So if let's say I remove the BR, how about that? Let's say I'm just going to remove the BR, okay? So basically I did a retrosynthesis of not having the BR, and let's ask ourselves, is there a way we can go in this direction to add the BR? Now the only way to know that is to know what directing effect each group has. This NO2 group is a strong deactivator, so it's meta-directing, which means it's going to go, should probably change the color. For the NO2 group, it's going to go at the meta positions. That's not where we want the BR. And relative to, let's just pick purple, this group, this is a moderate deactivator. So it's also meta-directing. And relative to this, this is a meta position. And this is a meta position. Right? So notice that none of these positions are where we want the BR, because don't we want the BR right over here? Right? That's not going to work out. So retrosynthetically, it doesn't make sense for us to remove the BR first. Okay? So we need to try something else. What if we, instead of removing the BR, what if we remove the alkyl group, or the, I should say, acyl group, not alkyl group, acyl group. Why don't we do that? Okay. Now, to go this way, we need to ask ourselves, okay, the only way we're going to get this group on is through a Friedel-Crafts acylation, right? Because this is an acyl group, so we need to do Friedel-Crafts acylation. But remember what we said, that we can't do an acylation with a strong deactivating group, right? That was one of the limitations. Let's go back again. You cannot do Friedel-Crafts in the presence of a strong deactivator. So that option is gone. So we got to think of something else. Well, what's the only other option? The only other option is removing the nitro group first. Okay? So can we get the nitro group going from here to here? Well, let's ask ourselves, the BR, is it a activator or deactivator? So remember, even though BRs or halogens are deactivators, they're ortho-para-directing. Remember that, right? So what is ortho relative to that BR? It's this, and this is the para position, right? And we want the NO2 at this position, don't we? We want NO2 at that position. So right now, this is looking pretty good, right? And if we really want to confirm this, we know that this group is a moderate deactivator, right? Which means if it's a deactivator, it's going to go meta to that group. And again, we have a favorable situation, right? Where we're going to get an NO2 at that position. So this seems like a pretty useful retrosynthetic strategy, right? Is to just go from here. Let me get my benzene ring back. Oop, wrong color. All right, so bottom line is we're going to add the nitro group last, okay? Now, the question is, which one of these groups are we going to take away next? Well, at this point, it's pretty easy, right? Because these groups are para to each other, right? They're para to each other. And what does that mean? That means the first group we should install should be an ortho-para director. And we know that the BR is an ortho-para director. And this group is a meta director. The ASO group is a meta director. So it makes sense, given that these are para to each other, to first install an ortho-para director, right? To then be able to get the other group para. So we know that we need to do bromination first. Install the BR as an ortho-para director to then get the second group on there, right? And then finally do a nitration to get the NO2 on. So why don't we draw that scheme now that we figured that out? So the first thing we told ourselves we were going to do is do BR2, AlCl3, to add a BR, right? And then the next step is we said we were going to do a Friedel-Crafts acylation. And there's no problem with doing a Friedel-Crafts acylation around a weak deactivator. Remember, BR is a weak deactivator. Halogens are weak deactivators, but they're totally fine when it comes to doing an acylation. And you know it's going to go para, right? Because the ortho position is just more crowded. And now, last but not least, you do HNO3, H2SO4 to get your final product. Because you know it's going to add at the ortho position of the BR. Okay? So hopefully that makes sense. You just have to practice this, right? I just did one practice problem, but here's some more practice problems, okay? Starting with benzene and using any other reagents, design a synthesis for each of the following compounds. Notice that each of these compounds have at least 3 substituents, right? This one has 4, but notice 2 of them are the same. Try to give these a shot using the logic that I used in the previous problem, the one I just did, to help you out with these, okay? So with that, that's gonna wrap up this video. Thanks for tuning in. I will add one more video related to nucleophilic aromatic substitutions, which is different from electrophilic aromatic substitutions. Not too much more, but I will have a small video regarding that, okay? So stay tuned for that. Thanks.